Okay, so now that we are familiar with the celestial sphere, the North Celestial Pole, the celestial equator, we understand those landmarks in the sky, we can move on to thinking about other ways we can navigate the sky. That is the topic of this lesson. So one way to find your way around the sky is by looking for constellations. Constellations are ancient groupings of stars that represents gods, heroes, shapes, stories, etc. Most cultures and people throughout the world have their own set of constellations and stories behind them. Today, when we talk about constellations, we generally talk about constellations derived from the ancient Greeks and Mesopotamians, but these are far from the only way stars have been grouped throughout history and throughout the world. Today, we have 88 official constellations. Originally, there were 48 constellations assembled by Ptolemy, who we will discuss a little bit later. These 48 are known as classical constellations. Over time, as more of the sky was mapped by Europeans, we kind of settled on 88 official constellations. So you might wonder what makes a constellation quote unquote official. Constellations represent shapes and stories, but for astronomers looking to navigate the night sky, it's more accurate to say that they represent regions. So there is an international body of astronomers called the International Astronomical Union. They're the body that's responsible for designating Pluto as a dwarf planet. So in 1930, they approved more or less this map of the sky that's on your screen. So each region hosts a constellation. So if someone says something like Jupiter is in the constellation Taurus, like this is what they mean. So Taurus, the bull, the constellation appears right here, um, somewhere in in this boundary, and Jupiter at that moment is passing through Taurus. That's what they mean. Jupiter appears in this bounded region, right? So constellations Gemini, they'll appear in this region. What are some others that are pretty cool? So you have Cygnus, the swan. Um, these regions are really kind of defined a little bit by the constellations that are in them. Um, but again, constellations, as we usually think of them, are kind of a connect the dots type of situation. These are actually like bounded regions that astronomers can use to kind of be a little bit more precise about the location that they're talking about. Um, this is not a perfect system, though. For example, there's the constellation Andromeda. So kind of this white region is its bounded area. We can see the actual stars kind of connected here. The thing is, and the Andromeda constellation shares a star with Pegasus, that constellation. And so that star is right here. So what constellation does this star belong to? It's a little ambiguous. So this system, not perfect, a little bit of an improvement, but not perfect. These boring bounded regions, though, are not like the fun way to identify constellations, right? The fun way is to look for stars, right? And how constellations are usually represented to kind of non-professional astronomers is either by connecting the dots or by some sort of intricate cartoon drawing. And you can see that sometimes it takes quite an imagination to kind of suss out what image the stars are trying to represent, right? So here we have Lyra, the harp, and the stars it's made of is Vega here, number of other stars that kind of make this parallelogram and a little hat right here. And this somehow represents a harp. Here is Scorpius. It's a little bit easier to identify as perhaps a scorpion, so it takes a little bit less imagination, but still it requires a little bit. Also, if you're looking to identify constellations, it has been my experience that different sources may connect the dots a little bit differently, right? These aren't necessarily, like wrong. They're just different interpretations. In my experience, though, they've always kind of included like the biggest and brightest stars in the constellation. So you still have that pretty much in common for through all the sources. There are sky simulation apps that you can get for free on your smartphone. So my favorite is um, which also has a browser-based version. So stellariumweb.org is the browser-based version, or you can search for Stellarium in the App Store. And it will show you kind of the connect the dots version and the cartoon versions of each of the 88 constellations. And it's actually a pretty good way for you to get kind of familiar with the shapes that you're looking for in the sky. Finding constellations can be a little daunting, actually, especially if you're in a very dark location. So you might think it would be easier to find constellations in a dark location without any light pollution. Um, But constellations tend to use pretty bright stars. So these stars are easier to see kind of in moderately light polluted areas than their dimmer stars. So when you're in a dark location, there are so many more stars. And for me, at least, it's really easy to get disoriented or have a hard time finding the bright stars you're after. So if you find yourself in a dark location and having a hard time finding constellations that you can find easily at home, don't worry, you're not alone. I also have this problem. But it is still possible, and I think my most successful method is to look for well-defined shapes within constellations. So some examples are Orion's belt, right? In Orion, you have this very distinctive three-star line. Um, so the Big Dipper is only a part of the Ursa Major or Big Bear constellation, but it's one of those that's a little bit easier to find. You see the Big Dipper here as part of the larger constellation. Or you can look for the teapot in Sagittarius, right? So Sagittarius is an awfully big constellation. And there's this nice teapot shape that can make it easier to spot um, than if you're just looking for the constellation as a whole. So these shapes within constellations are actually called asterisms. Asterisms can also be popular shapes outside of constellations as well. There's a popular one called the Summer Triangle that kind of connects three different constellations. Um, but it's not one of the official constellations, right? A lot of times these are mistaken for being the entire constellation. It's a little bit of a pedantic point, but looking out for asterisms can help you find the larger constellation and get oriented in the sky. When you're looking to identify constellations, it's really important to keep track of where you're facing. So if you're in the northern hemisphere and facing north, you will see several circumpolar constellations. We talked about that a little bit. These are constellations that are up all night, every night. So they appear to make a circle around Polaris, but they never go below the horizon. You'll see them kind of change orientation. So through the night, the Big Dipper will travel, and so it might end up being upside down above Polaris, but it's always up. It's always above the horizon. If you're not facing north, you're looking at seasonal constellations. So these are constellations that rise and set throughout the night, and they're usually only visible certain times of the year. So there are some constellations that will never, ever be visible to us in the Northern Hemisphere, right? Southern constellations like Centaurus and the Southern Cross, they're only visible really from the Southern Hemisphere, and we will never see them as long as we are in the Northern Hemisphere. There are 12 special seasonal constellations called the zodiac. So to understand why they're special, we need to recall what we know about the sun's path throughout the sky. So our solar system lies nearly on a plane. Like all the planets in the sun are sitting on a tabletop, right? So this plane is called the ecliptic, and it is bounded by 23.5 degrees on either side of that equinox path of the sun, right? Remember the equinox path um, is bounded by the June and the December solstice, right? That's where the sun appears. So planets also appear in this band because the solar system is more or less sitting on a plane. So the ecliptic also bounds the zodiac. So constellations that appear behind the sun or in this region are called zodiac constellations. So um, they're kind of oriented like this in the sky. They appear behind the sun from our perspective. So in this situation, the zodiac sign is Aries. So there are 12 of them, which is really handy because that means that we can kind of break the sky up into roughly 12 evenly spaced sections. And the sun takes about a month to go through each. Not exactly a month, but about a month. So the zodiac is, in some sense real. Like these are real constellations with some physical significance. They're located in like a conspicuous part of the sky. But it's far from governing your life through horoscopes, really. Um, in fact, there's actually a disconnect between your zodiac sign and where your constellation actually is in the sky. So whichever constellation is behind the sun when you are born is your zodiac sign, right? That's what we consider your zodiac sign. So these were mapped by Babylonians and Greeks 2,000 years ago. So in that time, our view of the stars has changed. So I've mentioned, I think in a previous lecture, that the Earth's axis is tilted, right, at 23.5 degrees from the vertical, and that it's always pointed in kind of the same direction. This is what causes the seasons. However, on kind of like longer time scales, um, Earth's rotation axis undergoes something called precession. It's like when you spin a top, you might notice that the handle kind of makes tiny circles as the top spins. So kind of like this schematic here. So we have a top, we spin it, the top of the top goes kind of in a circle like this. The same thing happens with Earth. It is spinning and it does a tiny little circle. The Earth will make one of these tiny little circles once every 26,000 years. So this means that Polaris will not always be our North Star, right? In 12,000 years, the North Star will be Vega. But it also means that our view of the zodiac has shifted as well. So if your birthday was in, say, like late May, you might think you're a Gemini, but the sun was actually in Taurus, right? It's pretty weird. Like this delights me, right? The universe is always changing. I think this is pretty cool. All right, so constellations are fun, um, but they may not be the best way to systematically map out and study the sky. But we've figured out a way to create a coordinate system to let us do this more repeatably, more methodically. So you're probably in some ways already a little familiar with this because you're probably a little familiar with GPS coordinates, right? The globe is divided into different longitudes and latitudes. So longitudes are these lines called meridians that extend north-south, that kind of mark locations east and west. Latitudes are circles that go around the globe and measure kind of north-south. I always remember the distance by um, the latitude. This is a ladder that goes from the south to the north. We do a similar thing with the celestial sphere. We divide the sphere up into longitude and latitude lines, basically, except we call it something different because we have to be difficult. So meridians of longitude are called right ascension. So these lines here represent right ascension. It separates the sky into 24 hours. So the units often used are hours, minutes, and seconds. The parallels of latitude are called declination. So astronomers call this dec, and they call right ascension RA. So the units for dec are degrees, minutes, and seconds. And like the latitude, it spans from plus 90 degrees at the North Pole, 0 at the equator, and negative 90 at the south. So if you use a telescope that tracks or has a method of automatically adjusting to see different objects, it uses RA and DEC coordinates. So a tracking telescope will follow the apparent rotation of the RA coordinate, which is the actual rotation of the Earth. So this is a picture of some people observing with the Braille telescope, which is the telescope on top of Roger Bacon Hall if you're on the CNA campus. I would look out if you're around. There's open houses throughout the semester. It's pretty cool to look through. That's just my plug for the Braille. So I want to use these last few slides that I have to talk about stars and how we name them and how we determine how bright they are. This doesn't fit neatly into another section, so I thought I would just talk about it here. So a lot of stars have traditional ancient names that come mostly from Arabic. Um, Examples of some big bright ones are there Betelgeuse and Rigel in Orion. There's Antares right here in Scorpius, Vega in Lyra. So if we did this for every single star, oof, that is a lot to remember, right? Something that can like narrow it down just a little bit is naming stars after the constellations they're in. So for example, Alpha Orionis is otherwise known as Betelgeuse. Beta Orionis is otherwise known as Rigel, right? These are two very bright stars in this constellation. So you might see stars referred to like this with a Greek letter before the Latin version of the constellation name, right? So Alpha and Beta are the Greek letters. Orionis is the Latinized version of the Orion constellation. How this generally works is that alpha is used for the brightest star, beta the second brightest, gamma for the third brightest, etc. So like up here, Bellatrix in Orion is Gamma Orionis. We have Zeta Orionis, Delta Orionis. The list goes on. But there are downsides to this. Like the most obvious being that we could run out of Greek letters, right? What then, right? What do we do? Another downside is that we could make a mistake in measuring the brightness of stars. So in this example, Rigel, we've discovered, is actually brighter than Betelgeuse, but it was still designated Beta Orionis. We also need a system for non-stellar things. Like there are things in the night sky that aren't stars, and we need a way to name them as well. So this isn't even a perfect system. Basically, there is way too much in space for us to give each one a bespoke name. So what you end up with are stars and other objects named for catalogs they appear in, right? Astronomers might decide like they're going to catalog a whole bunch of stars. Like that was what the Gaia mission did for Milky Way stars. They cataloged the locations and brightness of like billions of stars. This results though in something jokingly referred to as quote phone number IDs. They're called this because they tend to be kind of long strings of numbers that don't mean anything to you unless unless you know what you're looking at. Usually this is actually some combination of the date that this thing was observed and the coordinates of it, like the RA and DEC coordinates. Um, So yeah, for example, Gaia, like I mentioned, huge survey of billions of stars. They can't possibly name all of them. So they give each source a source ID as well as the RA and DEC and a bunch of other information, but they don't get kind of fun names like Betelgeuse and Rigel. There are also catalogs for non-stellar objects, so things that aren't stars. And a very famous one is the Messier catalog. So there was a French astronomer called Charles Messier. He lived between the mid 1700s and early 1800s. So his life's passion was to look for comets. He was a comet hunter. But he kept finding a bunch of other fuzzy patches, fuzzy objects that actually weren't comets, and he kept getting really, really annoyed. So eventually he started writing these objects down so he could avoid them in his search. And I kind of like to think of this astronomical catalog as fueled by spite. But it's a really cool catalog. It has staying power. So in total, there are 110 objects in the Messier catalog. There's everything from star clusters to galaxies to nebula to kind of the leftovers of supernova. And a lot of them have common names. Like here we have I think this is the Crab Nebula. Um, we have the Orion Nebula here. This is the Pleiades. It's a star cluster you can actually see by eye just without a telescope. Um, but some just go by their Messier number, right? So the Orion Nebula, for example, is called the Orion Nebula. People know what you're talking about, but it's also called M42. The Pleiades is M45. The Crab Nebula, M1. So some of these things have common names like that and a catalog name. Some just have a catalog name, and there's not any other ways to refer to them. Okay, so the last thing I want to talk about today is how we quantify brightness. Um, there's a traditional magnitude scale developed by Ptolemy where first order stars are the brightest, then second order stars are the next brightest, and so on until we get to about a sixth magnitude. This is really as faint as the human eye can see. Not everyone can even see this faint. I certainly can't. You have to have very good eyesight, but people don't see anything lower than like a sixth order star. It's been reworked and expanded over the years, though. We've found stars kind of brighter than what were classified as first magnitude, so we've had to add negative numbers to the scale. Um, but I want to note a couple of things about what you're seeing on the screen. So first, brighter stars have lower numbers, right? This is kind of counterintuitive. Um, but something with a magnitude of -5. So we've got Venus around a -5. This is brighter than something with a magnitude of 5. Really, the higher you get in magnitude, the fainter the object is. Second, this is a logarithmic scale. So something that's a magnitude 2 is not half as bright as something that's a magnitude 1. It scales differently from that. It's mathematically more complicated, but it actually tracks with how your eyes view brightness. You notice differences in brightness logarithmically. So it's natural, you don't have to think about it, but this is a logarithmic scale. Okay, so I think that is it for this particular lesson. Again, check out the demos, check out the optional videos, take the quiz, do the assignments. Let me know if you have any questions.